Okay, let's start today's lab class. This is a heat transfer lab class, which you might have seen in your timetable. Yeah. Yeah. Thank you, Morgan. Yes, good. We will go into, I'm going to introduce to you the number of experiments that we will be doing. And I will also tell you how to do a emissivity experiment in today's class. We are going to do it in a virtual simulator, and you can find the values there, and then you can upload it to later on in the LMS after doing it. It just takes hardly few minutes. Okay, so it's not tough. Okay, let me first tell you what are all the experiments that we are going to do in this lab. Now these are the set of experiments. As usual, we are going to talk about the three modes of experiments, which will address the three modes of heat transfer: conduction, convection, radiation, and heat exchangers will be there, and application of these in the cooling and heating systems, right? So we have thermal conductivity study in guarded plate, and you have in a pipe insulation using lagged pipe. Guarded plate and lagged pipe will have conductivity, thermal conductivity measurements, and heat transfer coefficient, natural convection in a vertical cylinder. Similarly, that is on convection, and we'll have forced convection, natural convection. Then we have composite wall, thermal conductivity of insulating powder. Okay. Then we have natural and forced convection in pin-fin apparatus. Then other two are radiation, Stephen Boltzmann constant and emissivity measurement in radiation measurement in radiation heat transfer, and application of that in a heat exchanger. So we have both parallel and counterflow heat exchanger, a simple tube-in-tube parallel counterflow heat exchanger. We will study how much it is being transferred, LMTD, all that in that. Then cooling side, we will be having a simple refrigeration system which uses conventional refrigerant and as well as hydrocarbon refrigerant. Okay, then you have an air conditioning where we call psychrometric. Using a psychrometric chart, we will conduct air conditioning test. Then we have fluidized bed. How does a cooling tower operate? Is a small cooling tower. How does the temperature variation happens along the height of the cooling tower? It's a fluidized bed cooling tower. So these are the experiments that we have. So if you count natural and forced convection as two different experiments, closer to 16 experiments will be there. Okay, so there will be at least 12 experiments that you will definitely will be doing. If there is time, we may go on to complete all the 16. Otherwise, probably we may stick with 12 experiments. Okay, that is about total number of experiments that you will be doing in the present semester under heat transfer lab. Okay. Now, today's experiment is about emissivity. The reason why I've chosen this is it is easier, and we have the link to do the simulation in the place wherever you are. So we have taken emissivity measurement as the first experiment. Okay. Now, let us just a short introduction what emissivity is about. Any surface, if you have, okay, when the amount of heat reaches, the surface on the top of the surface, or the area of the surface which receives heat. Okay, that is called incident radiation. Amount of heat coming by the way of radiation is called here incident radiation. Of that total radiation, depending upon the material nature and type, we have a part of it will get reflected, part of it will go through it, will be transmitted, will go through the material if the thickness of the material is too small and transparent. If the thickness is too high, then probably this transmission may not happen. And whatever is retained, whatever is remaining, whatever is not reflected and transmitted, remaining gets absorbed in the system. That initially results in the increase of temperature. When the object is at a lower temperature than the amount of radiation that it receives from the source that it receives, obviously the temperature will rise, but eventually steady state will be reached. If the radiation remains steady constant, then the steady state will be reached. When an object is at any particular temperature, what happens, as this we have seen in the introduction class, radiation occurs in all objects above 0 Kelvin. That we know for sure. Okay, only thing is they are not significant unless they reach very high temperatures. But there is radiation at all temperatures. Okay, so the amount of radiation leaving from the surface, from the material, okay, from the surface due to this temperature, that is what is called amount of radiation being emitted, emissivity, the ability of the surface, ability of the material to emit energy. Okay, that is measured as in the terms of emissivity. Okay, then why is the term emissivity? You know that black body is the object which can emit or absorb, it can absorb all the radiation that falls on it, and equally true, its emissivity is also 100%. That is taken as reference. A black body's emissivity is the is emissive power, the ability to radiate energy out of it. That is highest in a black body. So we consider that as the maximum, that as the 100% efficient radiation. So we give the term 1. So the emissivity varies from 0 to 1. That term in 1 is given, the value 1 is given to a black body. Okay. Now all other objects are measured in comparison to that black body. That means how much is the amount of radiation that the material emits compared to how much it would have emitted had that been a black body. If the same material has been a black body, how much it would have emitted, but being the present gray body, how much it is emitting. So that ratio is what is called as emissivity. So that is given in terms of words, in words here. It is defined as the ratio of energy radiated from a material surface. 1 minute. I'm getting some chats. Am I not audible? Will all this phenomena occur at the time, sir? Is it like Carnot efficiency? Good afternoon. Yeah. See, in a normal material, all these things has a possibility of happening. Definitely absorption reflection will be there, but maybe very small amount. But the transmission depends upon the type of material and the thickness of the material. See, if that material is too thick, I don't think heat can transfer through it. It gets absorbed and then it gets emitted. Okay, if the surface, depending upon the type of surface, how, whether it is polished or it is rugged, based on that, whether it is oxide layer is present, no oxide layer is present, based on that, the amount of radiation that is reflected will vary. So the amount of radiation that is come in, which is equal, this 100% equal to the addition of all these three. So at one point of time, you can totally make sure that something is not being reflected by putting over layers of glasses, which can reduce the short wavelengths. Now this we will study in detail when we go into radiation. Okay, so don't worry. We will study more about this when we go into radiation. On a material, if the properties match, if the size of the sample allows it, then all three can happen. Yes, black body is like your Carnot efficiency, which is the maximum, and every other thing is measured against Carnot efficiency when it comes to thermodynamics. In terms of efficiency, same way, everything is measured against black body when you come to radiation. Yes, you're right. Okay, so if it is the ratio of the energy radiated from a material surface to that radiated from a perfect emitter, which is nothing but a black body at the same temperature.
So,
Yeah. Yes, ma'am.
so emissivity, the total amount of energy that is like we calculate for emissivity will be reflection plus transmission, isn't it?
No. That is not. That is entirely different. What you see here, reflection, absorption, transmission, is entirely different from what I'm talking is emission. Right? Emissivity is big amount of energy that is coming out of a surface because of its temperature. It is not what it is reflecting. Right? A black body, when it is steady state, it actually it receives 100% of all that is falling on it. Nothing reflected, nothing transmitted, everything is absorbed. Because it is in steady state, whatever heat it is receiving, it also has to emit. Then only then the temperature can remain constant. If there is a difference between that, then there will be a change in temperature. Then it's no more a steady state. In a steady state condition, whatever heat is falling on it will be emitted back. Emission is different from reflection. No, reflection is different. Reflection, see, any amount of heat which is directly reflected is not going to contribute to your emission. Emission is because of the amount of heat that is present in the object. Am I clear?
Thank you, sir.
Yeah.
Sir,
Yes, man.
sir, do you mean to say that emissivity is a function of temperature?
Yeah, function of temperature and wavelength. Yes. Okay,
Okay.
that's what is shown here. See, it is at what we have to talk about at the same temperature and wavelength under the same viewing conditions. Viewing conditions means the atmosphere surrounding it and how much we are exposed to that particular object's surface. We will study. You know all these things once we start radiation chapter. You will be able to understand this, because when you maintain the objects in two different temperatures, then obviously the amount of radiation that it is emitting will be entirely different. And also, when radiation comes in different wavelengths depending upon the range in temperatures, okay, that also we will see when it comes to. So each temperature has its own variation in wavelength, and there will be a one peak wavelength for every temperature, or otherwise every wavelength has got one peak temperature. These things are properties of materials. Okay, radiation properties, we will study all these things when you come to the class. So just understand these parameters are there, these things are linked. Okay, emissivity is the amount of energy that is coming out in relation to its black body. Okay, we are not we here we just need to understand how much energy is coming in, how much energy is going out. Once I explain the experimental setup, you will understand what is happening in the setup much better. So just wait little longer to understand. Okay, some more details about emissivity. Emissivity of a surface depends not only on the material, but also on the nature of the surface. You can have the same materials with different surface properties, then you will definitely have different emissivity values. For example, a clean polished metal surface will have low emissivity, whereas a roughened oxidized metal surface will have high emissivity, because there will be more points which can able to transfer heat. The emissivity also depends on the temperature of the surface as well as wavelength and angle at which the heat is falling or we are viewing. All these things we will see them when you come to the class. So just understand, because I cannot take entire radiation chapter here. So I just want to make you alert you to the terminologies that we may need to know when you go into experiments. Just understand the experiment now. When you come to radiation chapter, you will be able to relate them and understand much better. Okay. Now this is the setup that is there in our laboratory. If you come to our lab, and if you want, if you all you will be asked to do experiment on this experimental setup, exactly this is what is there in the simulator also. So that is to give you an encouragement. So the what is there in a laboratory is not different. Okay, so now you can see this is a laboratory setup. You have a black body and you have a test piece. There are two pieces are present in this. Okay, so we are going to compare the emissivity, that means emissive power of a test piece with a black body. Okay, now these are dimmerstats which are used to control the voltage. So what we are going to do is that you are going to apply voltage to the we are going to give electrical energy to the plates, equal amount of electrical energy, and try to measure the temperature here. We will try to measure the temperature of these two plates for a given amount of electrical energy. That is a measure. Okay, so we know we'll be able to once we know the temperature, amount of energy given, from those two we can apply formula, and we can directly find out emissivity of a unknown object. Okay, by equating these two, we will tell you in the next slide. So this is the experiment. You have dimmerstats. Each one is to apply for a black plate. You have one dimmerstat and one for a test plate, and you have temperature reading panels here. Okay, so you just have to switch on. Once you give electrical energy, probably you may have to wait for around 15 to 20 minutes depending upon the amount of energy that you are giving. Okay, for the temperatures to stabilize. It will be at room temperature initially, and it will rise until the energy that is given okay, heats up the plate, and there is a radiation heat exchange between these two surfaces, and there will be a steady state where the temperature of the surfaces will remain constant. Okay, temperature will reach constant. Need not be same temperatures. They can be different temperatures, but the temperature will be constant at that point of will be constant for the given energy input. Once you know the temperature, once you know the energy given, I can calculate emissivity with the formulas. Okay, just wait, I will explain it here. Now this is the details of the test plate in our laboratory. So you have a test plate and you have black plate and you have thermocouples attached to each one of them, T1 and T2, and you have T3 attached as the your atmosphere or the surroundings temperature. Okay, so there are three temperatures are given. You have two thermocouple plates are given. The only difference between the simulator and our setup is we have only one thermocouple. They have three thermocouples. Doesn't matter, all three thermocouples on any plate will give you the same temperature. There won't be any variation because we are concentrating only about steady state conditions. So obviously temperature at any point in this plate will be same. So the simulator will give you three temperatures for test plate, T temperatures for black plate, all three will be same. Okay, so wait, so these are the links. The link is there in your manual also. I uploaded the manual in your LMS. All these things are already uploaded in your LMS. Okay, so this is a general link, and for the emissivity experiment, this covers the theory, and this is the experiment that we are going to show you the simulator that I'm going to show you. So it is there. Anytime you can check. Now what is happening here? Now just if you listen here, there are two plates here. Let us take this as the black body, surface B, and surface A is the test plate. Okay, so you are giving energy to both of them. That means both of them start to exchange heat among themselves. And what will happen when you give the amount of energy that is once the plate is heated, once the plate is at a particular temperature, what happens? The amount of energy emitted out of it is defined by emissivity, Stephen Boltzmann constant, into temperature of the plate minus temperature of the surrounding. Okay, sigma eta sigma into T power 4 minus T atmosphere power 4. This is from single plate. This is a test plate. Similarly, you take the plate, black body. For that also, emissivity of black body is 1. Stephen Boltzmann constant, temperature of the black body at that for a given amount of voltage and current, and temperature of the surrounding. So this is the amount coming out from the black body. This is the amount coming out from the test surface. Now, if you give instead of allowing that to have its own energy, you are trying to do the reverse way. You can do the experiments in both ways, meaning that you can adjust the dimmer stats of each plate and maintain constant temperature TP, temperature of the plate as well as temperature of the black body to be equal. For example, you can set both of them at 75 degrees Celsius, both of them at 100 degrees Celsius, both of them. And once you know both, once you set up both of them on equal, then this terminology and this term will be equal. You can cut it off. Emissivity of black body is 1. And from that, you will be able to find, you know how much energy you are given in the dimmer stat, how much energy you are given in the for the plate. From that, you can find out unknown value of emissivity. That means you know all these values. All these temperature values are known. You can read it from the thermocouple. Okay, the reading. All 4 temperatures are known. 3 temperatures are known. Emissivity of black body is 1. Stephen Boltzmann constant is constant. That also we know. And this Q for the test plate and Q for the black body is what we gave. So that also we know. So only thing that is unknown in this case is emissivity of the test plate. So when you equate these two, you can find out directly what is the emissivity of the plate, test plate. That is the logic that is being used here. Yes, Mohan.
Sir, what about the surrounding temperature?
Yeah, that is what is there as a TC.
That will be
when that
equal.
No. That see because depending upon depending upon the material. See, if you have a gas, if you have any particular gas, you wait for that to reach a particular temperature. That's all, the steady state temperature. Once it reaches that, what happens is once it reaches steady state, it means that whatever heat is coming in is lost. There is a thermal equilibrium has come. In that particular sense, a solid and a gas need not be with the same temperature. When it will be in the same temperature, right? If your entire thing, uh, gas, entire gas in that surface, if you maintain it at a particular stagnant, if you can maintain it really stagnant, then probably you can achieve the same temperature, which we are not going to do. That is not our objective. Yes.
But in that experimental setup, both the bodies are there in the same thing, no, sir?
Yeah, but both of them exchanging heat with what? They are exchanging heat with the surrounding atmosphere only, right? The TC.
Yes.
Then
Yes, sir, yes, sir.
yeah, as long as that temperature is constant, anyway these plates are not facing each other. In our experiment, they are kept horizontally. They are not facing each
Yes, sir.
other. So the only thing that is exchanging heat with the rest of the atmosphere. So we have to only include the temperature of the plate and the atmospheric temperature, nothing else.
Okay, okay, sir.
Yeah.
Got it.
Yeah. Okay. So now let me just go to the simulator. No, it may look a little different because you are both learning the theory now as well as experiment now. So it may look little, you may have certain doubts here and there, but by the time we finish this demonstration, you will know clearly. Don't worry. We have just finished half of it. Now this is your simulator. Hope you can see it. All right. Oh my goodness. I'm not able to. Okay, let me, yeah, this is much better. Okay, yeah, hope you can see that. Now this is, as you say, you can see this is the exact setup that we have in our laboratory. Only thing is the position where these things are placed are entirely different. See, these two are placed little far, that's all. Then you have a single switch which has got, which is controlling where the energy is going. Now we have two plates. You have a black body and you have a test plate. Okay, now we are going to apply heat energy to the black body and to the test plate. Okay, and then we are going to allow them to come to steady state, and then we are going to equate the energies. Okay, let's just wait. Now here you can choose the material here. These are the options that they have given. It is inbuilt, so we have to only play with any of these objects. So let us take aluminum. You can take anything, and if you can change the diameters of the plate and thickness of the plate. What happens when diameter of the plate changes? It only changes the area, surface area. Okay, but anyway they are going to get cancelled because you're going to have same amount of surface area for both the plates. Okay, so if you want, you can try different areas and different thicknesses also. Obviously you are going to give the chamber temperature. What will be the chamber temperature? You can give -20, you can give 0, you can give atmospheric temperature like 35, like that. You can give any temperature that you can give, because whatever temperature you are giving here is what is going to be, it's going to get, it will be maintained there. Okay, now let us talk about, okay, now you can see here, this is the switch. Okay, um, which talks about whichever plate that you want to apply energy, it should be on that end. Now this is black plate, this is test plate. It is on the top. Now when you apply energy on the black plate, energy will flow to the black plate by that. If you want to do it for a test plate, you just click there. You can see that will flip down. Now it is, energies are connected to the test plate. Now you can apply voltage. Now the test plate will get heated up. Now let's go for start with the black plate. Black plate, let us apply same power. We are applying 100 volts and 0.2 milliamps, 0.2 amps of energy. Okay, now you can apply, as I said, you can apply two different values. Now this is for, we have applied it for black plate. Now let us do it for test plate. Now it's see, all of them is 0 because it is in test plate. Now let me just click this once, right? The dimmer stat, when I click here, again it has come to 100 volt and 2.2 amps. As I said, you can keep both of them equal amount, or you can keep different amount of energy. Okay. Only thing is you should be able to substitute proper values in the equation. That's all. The experiments can be done in any way with the same, both of them, both plates receiving same energy, both plates receiving different energy. You will definitely get the same emissivity value. Okay. Now these two we were given. Let us switch it on. Now this is the power. You can see here, just like how it is there in our home. You can switch it on. Now you can see, we said generally it takes 15-20 minutes for the temperature to get stabilized. So being a simulator, it is fast forwarding that 20 minutes. In your laboratory, you have to sit and do your calculations or do some other procedural writing in this all these 20 minutes, because you are going to do nothing. You just go check, come back, whether it is stabilized or not. You will be going and coming back, seeing what is the temperature. But it will anyway, yeah.
So how to check it if it is stabilized or not?
Yeah, wait till I'll tell you. Once it stabilizes, I'll tell you. You can see the temperature is moving. You can see the temperature is moving. In your laboratory, if you come and turn to any temperature, T1 and T2, T3, or T1 and T2 especially, T1 and T2, any temperature, at least it should remain, it will keep changing. You know, if you give it 5 seconds, 10 seconds, even 2 seconds, the temperature will keep rising. Right? There will be a time it will not rise beyond that. If you keep recording the temperature against time, for 5 minutes, let us say the temperature will be 40. For the 10 minutes, the temperature will be, say, for example, 75. 15 minutes, it will be, say, for example, 110. 20 minutes, it will be again 110. That means you know that the temperature has stabilized. That is how you will understand, you will identify the stabilized in the laboratory. But here, after 20 minutes, once it will automatically stop when the simulator will stop when the temperature reaches a stable temperature, constant temperature. Okay. Now T1. Okay. This is, you can see here, they have marked what is T1 and T2, T3. T1, T2, T3 are temperature that belong to the black body. T4 is atmosphere, the surrounding temperature. T5, T6, T7 are test plate temperatures. So in your tabulation, I have shared a document in your LMS. It has got a tabulation. That tabulation, you can just go there and you can, against each value, how much voltage you applied, how much current you applied, what is the material you have chosen, and how much is the temperature, what is the temperature on each thermocouple. All those things you can record in the observation table. Okay. Now this is T1. If you want to go to T2, just click here. T2. Here, there is an arrow here. T3. You can see that because T1, T2, T3 all belong to the same black plate, all three are having the same temperature value. You see, T1, T2, T3 all having the same value. Now if you go to T4, it will change because T4, T5, T4 is atmosphere. T5 will again change. T4 is just, it is where we are, what we gave. It is at the same temperature because that is, we know that is atmospheric temperature at that point of time. Now we have T5, that is the temperature of the test plate. T5, T6, T7, all three are temperatures of the test plate. They will be constant. Okay, they will vary only when the material is still under heating condition. When it is keep on, it doesn't reach the steady state. It's just adding heat to the plate. Once it reaches steady state, all the temperatures will be same. So you got 3 temperatures constant, other 3 temperatures constant. Now you know the stabilization has occurred. Now in this case, you don't have to calculate. Now here, because it is a simulator, it also gives you a result. But in your observation, you have to put an observation. You have to maintain an observation. That you should remember. Okay, that will be subject to physical verification when you come here to the laboratory for examination or for any other final evaluation purpose. Probably you may have to, like how you submitted your CAT exam answer sheets. You just have to scan the tabulation parts of all the experiments, and probably finally you may have to upload. Some way you will be definitely asked to submit. So please maintain a observation. In that observation, there is a formula in the document itself, in the LMS our document itself. You can apply that formula and you will get the value. I will also show you. Don't worry, I will also explain that to you. Okay, now for the simulator, steady state has reached. You just click show result. It will show you the value here. You can see 0.77 is the emissivity of the test plate. You can't find it in LMS. Okay, wait, let me, I'll come and I'll let me check after this over. Let me go and check. Okay, so 0.77 is the emissivity of the setup. Now let me repeat the same experiment with another material, so that those of you who missed, probably you can just check whether you're able to follow or not. Every time you have to reset it, it will reload. Now let me go with the steel. I'm taking steel as my material. I don't want to change this material dimensions. Chamber temperature can be as it is, or I can try to bring it to 20 degrees Celsius. Okay. Now for a black body plate, I'm applying energy. Okay. So 100 volt to 0.2 amps. Then I'm flipping the switch and going to the test plate, and I applied energy for the test plate, and I fix the values. I'm switching on the system, and the system runs, and it will definitely take 20 minutes for it to come to a stable temperature. Okay. If you try to record in your observation after every 20-30 seconds or 1 minute, you will also get the same kind of temperature variation in your observation also. How the way that it is increasing, you will have the same increasing value. Generally in our laboratory, we won't give 100 volt. We give only 35 volt, a very lower volt, because otherwise if the amount given is too high, the temperature that it reaches is very high, and the time that you have to wait will be very, very long. So we give very small amount of values, and we try to finish the experiments within the given time. Even for that itself, you may have to wait for 1.5 hours. So in our laboratory, we give 35 voltage as the smaller voltages and smaller amperes. Okay. Now you can see it has reached the stable state. If you want, you can check all the temperature values here. Everything is as it is that we have given. And now if I show result, just check the result, and the value is 0.85, you can see. So that is the emissivity of steel plate. Okay, that is where given. So it's just an approximate understanding of how to conduct a setup in a emissivity apparatus. Okay. Okay. Any doubts in this simulation? After this I'll go and close to your doc. I want to go explain to you the document. Any doubt in the simulator? Now what you are going to do is, you are going to do it for 2 materials, and then you are going to calculate it and substitute in the tabulation that I will show you. And that tabulation alone you have to upload in intranet. Not everything, just the tabulation alone. Okay, in your observation, maintain the tabulation, calculation, and result. That much is sufficient. You just maintain the tabulation. That page alone you just scan and upload in the LMS. I'll show you what tabulation I'm talking about. Okay, no doubts here. Right, good. Let me come to, it's a file open here. This is the document I was talking about. Hey Pavitran, என்னடா lab explain பண்ணிட்டு இருக்கறியா? Right. Okay, this is the document that has been uploaded in your intranet. You can see now. Okay. So this gives you the link, the simulation link that I have shown you. Okay, as well as the procedure. what is the theory, and see, this is the voltage that you give, that 100 volts and zero point 0.2 ampere. That is what you give here for both cases. If you give different values, you substitute whatever value that you are giving here. You will have W1 as the power input given to one plate and W2 as power input given to another plate. Okay, so you can have two different values, you can have same values. In whatever value you get here is what we're going to use in the later on stages. Once you substitute here precautions and procedures are given. Now W1 is the amount of energy you can see here given to, let us say, black body. Okay, yes, black body, and that is nothing but eta, emissivity of the black body into Stephen Boltzmann constant in temperature difference into area. So this is this goes, the amount of energy given is translated into this much amount of radiation, because we have eliminated conduction perfectly. It is not in contact with anything. We have eliminated convection. There is no real flow of anything is happening. Whatever is there, it is in a concealed room. Okay. Now we have here black body, sigma, and the area into the temperature difference between the black body temperature and the atmospheric temperature. Now same thing is true for a test plate and test plate into atmospheric temperature. If you these two, if you have given W1 is equal to W2, you can just use this. If W1 is equal to W2, then these two will be equal. From that, emissivity of a test plate can be found out, because everything else is known. Black body temperature we have found out. Okay, all three temperatures are pointing T1, T2, T3, black body temperature. All three will give you the same value. Again, T5, T67 is test plate temperature. All three will give you same temperature. So you can take any one of that, and that will be your black body temperature. That will be your test plate temperature, atmospheric temperature, ambient condition temperature you have given, that you know. Emissivity of black body is 1, that you know, and the emissivity of the test plate can be found out. Okay, that is the way this experiment is done. So depending upon the material, temperatures will be different. You can try two different materials. This is the tabulation that we are talking about. So serial number 1, 2, you can do it for same plate. You can do it for two different powers. One giving 100 and 0.2, or 150 and point something. So whatever, you can give two different values. That is up to you. But I want for two different materials, I want you to perform this test and then record all the temperature values. Okay, and then tell me what is the emissivity that you get. Okay, and that you get. So the result will be emissivity of the test plate found to be A, plate 1, B, plate 2, whatever material that you have chosen, and give us the value. Take a picture of this particular table and result. That alone you can upload in LMS. This is the document that will be there in LMS. I don't know why you're not able to see. Probably in the participant list, you may need to be added. That I will do it now. Okay, any doubt in this document? This is your experiment number 1. Date will be today's date, and you have to maintain this observation. So download this, keep a soft copy of this, so that in the last time you can just take a printout and keep it in your record if you have to submit it. So this tabulation should be there in your observation. Please maintain observation. I repeat, you will be definitely asked to submit, because everything is going to be virtual. Some proof needs to be shown at the end. Which material is used in lab? We are using aluminum, but surface finish will be different. So the value of emissivity will be much less in what we are using in our laboratory, but it's aluminum. Okay, though as I said, though material is same, because the surface finish and oxide layers and many other things are change, many other things can change, you cannot really say that it will have the same emissivity value. So any emissivity value can come. So we have to really perform the test and tell us what is the value. Okay. Okay, any doubts in this document?
Sir, sir.
Yes.
Sir, should we take printout in that record sheet or in the airport sheet, sir, for maintaining record?
I'm not able to hear you, but if I heard you rightly, you're asking whether should we take a printout and keep in your observation. Now you don't need to take any printout. You just have to draw the tabulation in your notebook, in an observation notebook. This tabulation alone You just draw this tabulation alone. In the next page, just write the formula and model calculation. Just 2 pages. 1 page is you have the tabulation, record the values. Another page you have formula, experiment name, and then you have formulas, model calculation. Just maintain these 2 pages alone. Okay. To me, you just send only the tabulation part alone. The tabulation part alone, you just take a PDF. That page alone, you just upload it in my LMS. You don't have to take any printout. Printouts, we will see how, once when the college opens, when the examination comes. After seeing the situation, we will see in what format we have to submit. Okay.
Thank you.
Yeah. Okay. So anything else in this document? Okay. I hope now you got some idea what we are talking about. Now we'll come back to the slide. Okay. So what you need to do is you just set. So I have shown you what is there in our, now I'll show you back again what is there in the laboratory. You can see it is same as the simulator. Only thing is this is there little closer. They are arranged a little differently. It is the same experimental setup that we have. So you will not find any difficulty even if you come to the laboratory to do the experiment. Okay, it is the same. Okay. Now the procedure, just choose a material and size. As I said, 2 materials. Select the ambient temperature. Do the experimental procedure. The same procedure is also there in the document also. If you want, you can read it again. And then tabulate the readings. Find the result. Make model calculation. Write the formulas on the side. Then upload it in the LMS within 3 days. In fact, as I said, as I demonstrated, you will do it within 5 minutes. All you will take is 5 minutes. And to make the tabulation and write it probably another 10 minutes, and to upload another 10 minutes. You may not need more than 30 minutes to, even if you slowly do it, you may not need more than that. You can submit it in the LMS page within 3 days. I gave you 3 days time because you can easily do that. Maintain the observation record for later physical verification. That is another instruction that you need to know. Right. So with that, whatever I wanted to convey today has been done. Okay, if you have any questions now, you can ask me. The theory part, you will have questions. What emissivity is, what is emissive, what is going in, what is coming out. That part you will be able to relate this experiment when we teach the radiation unit. So don't worry. Even if you have some doubts now, it will be clarified then, because there are some more details that you need to talk about. What is black body? What is gray body? Why there is difference? What against what they are actually exchanging heat? All those things you have to be dealt. Once we see that, small doubts that you had here and there will get clarified. Yes, any other questions? Mohan, yeah, your hand is still raised. You have another question, or that's for old one?
The old ones.
Yeah, yeah. All right. Okay. So let us go into attendance.